So let us start today's session. And hello and welcome to this NPTEL TA session on Fluid Flow Operation course. And myself, Aman Das, and I'm a research scholar from IIT Kharagpur. And today we will be discussing some questions related to week 9 course content. And the content is mostly we will be discussing some concepts related to dimensional analysis and law of similarity. Okay, so let us start. Let us see what are the different concepts and then we can solve some questions. So in here, we most of the contents are about some introduction to what is dimensionality or dimensional analysis similarity, and what do you mean by homogeneity of dimension, what is the Rayleigh method and dimensional analysis, what is Buckingham's pi method of dimensional analysis. So you see, in modern engineering, like the work mostly engineers do, uh, the fluid or the flow behavior is generally very complex, and it is very difficult to get a complete theoretical expression of what we are trying to achieve. So it is not very well possible to get a complete theoretical side of any particular system. So you see, the complex flow behavior is accounted with where often a purely theoretical investigation failed to yield a practical or workable solution. Even if we, let's say, assume something and derive an expression, but that becomes very unpractical. Like the expression we get couldn't able to predict the mm, parameters that we are investigating very well. So in such a case, the dimensional analysis actually plays a very significant role to let us know what are the different parameters on which this particular dependent variable depends upon. Okay. So the dimensional analysis deals with a method for reducing complex physical phenomena to the simplest and most economical form prior to obtaining a quantitative solution. Okay. So suppose we have a complex phenomena and we now know that these are the parameters on which this particular dependent variable will, depending upon these independent variables, this is the variable that will change. So it is now mostly economical because we know that what are the parameters we have to vary and then see what changes we are getting. Now, this principle of dimensional analysis and dynamic similarity are extremely useful in the use and interpretation of experimental data. So as we have discussed, that we can now predict the experimental data very well. Uh, like in 1969 around, Bridgman uh, wrote this something. This principal use of dimensional analysis is to deduce from a study of the dimensions of the variable. Like we know the dimensions of the variable, and from there we will be deducing something. In any physical system, certain limitations on the form of any possible relationship between those variables. Okay, the method is of great generality and mathematical simplicity. Sometimes experiment cannot be possible to carry out its full size units, as we have discussed, when the experiments are carried out, like for example in dam, river, channel, or hydraulic machines such as turbines, pumps, etc. We cannot directly possible. It is not possible to carry out experiments directly, go into the dam and measure flow rate or something. It's very difficult. The sake of economy and convenience, it is required that small scale models are made for test purposes. Okay, certain laws of similarity must be followed in order to ensure that the model test data should be applied to the prototype. So when we now we have generated a small model in which we will performing the test, but after we scale up, it should be such that the values or the parameters we are getting or the dependency we are getting, the same dependency we can expect from the prototype as well. That is when we scale up to a bigger scale. Okay. So in order to apply these laws of similarity, one has to express the experimental results in terms of non-dimensional factors. So the dimensional analysis and dynamic similarities are useful in finding such non-dimensional factors. So say we have a blading of a hydraulic and steam turbine are tested in a wind tunnel where air is used as a fluid for the experiments. The results are there converted to work with machines with water or steam as the case may be. For example, say we have steam turbines and tested in wind tunnels, but it is very difficult to replicate those. It is very difficult to perform experiments in those conditions. So what we will be doing is we will be making a model in which instead of using air tunnel or instead of steam turbine we may work with water, for example, another fluid we may work with. But then we can, from these experimental data, we can then revert back that okay, we can predict okay, these are the things that will be happening in the actual hydraulic or steam turbine. And this is possible by applying certain laws of similarity with the help of dimensional analysis. Okay. Now, these are something that we need to understand. To assess or measure an unknown quantities, we should have the acceptable units. There must be different standard of units as per the definition and convenience to assess the quantities, out of which a small number of basic quantities has to be considered as standard quantities and they are expressed in terms of basic units. For example, the basic quantities are called fundamental quantities, which only three numbers, say mass, length, and time, generally expressed as ml and t. There are other things could be, but for now, in this case, we will be studying only three number of quantities, basic dimensions, fundamental dimensions. Okay. All the other quantities, let's say area is nothing but as an unit or expression of length times width, which is nothing but length square. Similarly, volume is nothing but length cube. Velocity is nothing but length by time. Acceleration, similarly, length by time square, and so on. And each can be expressed in terms of the fundamental units, and therefore they are called derived units and found by multiplying or dividing the fundamental units. Okay. So first we have is the primary fundamental units, which is the length, mass, and time, and then we have auxiliary fundamental units. Okay. Say a measure of certain physical quantities like electrical, thermal, or illumination and elementary particle are all represented by fundamental units also, and these units are used only when particular cases are involved. Okay. uh, they will not be coming everywhere, so only when we analyze particular systems, specific systems, these terms will be coming. So these are called auxiliary fundamental units. Sometimes some engineers also prefer to use quantities which are easier to measure. Okay, like mass is something that is not very easy to measure. Rather, we measure weight. So that is called nothing but force. So it is called a convenient fundamental unit, but it's not actually a fundamental unit. Okay. And these are different important quantities with dimensions. You can see length has dimension L, unit is meter, time seconds, mass m, kg, temperature in Kelvin, current in amperes, number of elementary particles in mole, and some luminous intensity as CD or candela. And in geometry, we have area, volume, moment of inertia, second moment of inertia. Kinematics, we have velocity, acceleration, angle, angular velocity, quantity of flow, mass flow rate, etc. Similarly, in dynamics, we have force, moment, torque, energy, work, heat, power, pressure, stress, etc. And similarly, fluid properties, we have density, viscosity, kinematic viscosity, surface tension, thermal conductivity, specific heat, bulk modulus, and more. Okay. So now let us start and study. Okay. So there are essentially two-dimensional analysis method. One is the Rayleigh method or Rayleigh method, and one is the Buckingham Spy method. And both of them give us fairly one approach to obtain the relationship, and we'll see how it is done. So in Rayleigh method, the method is based on the fundamental principle of dimensional homogeneity of the physical variables. The dependent variable is identified and expressed as a product of all the independent variables. And this is all the independent variables raised to some unknown integer exponent, let's say ABCD, that we don't know, and we will be obtaining that. And equating the indices of n, fundamental dimensions of the variables are involved. N independent equations will be obtaining. And from these n equations are solved to obtain the dimensionless groups. And similarly, in Buckingham Spy theorem, Buckingham Spy method, uh, we will be creating dimensionless groups, and we will be finding a relationship between the dimensionless groups. So one important thing you can see it is written below is that both Buckingham's method and Raleigh's method of dimensional analysis determine only the relevant independent dimensionless parameters of a problem, but not the exact relationship. It will tell us that this dimensionless parameter will be dependent upon this parameter and another parameter, but not exactly like up to what power, like to the power 3 by 4 or 4 by 5. We can't exactly get a exact function of what we will get, but it can tell us that okay, this will be dependent upon these parameters. Okay, this, so that we can get from here. So let us try to start. Let us start with the Rayleigh method. Okay. So we'll see how it is done, and then we'll try to solve some questions as well. So here you can see the method involve the following steps. Note all the independent variables. Okay, let's say we have y, and y is actually dependent upon function like parameters like x1, x2, not that many parameters, independent variables. So first we noted down all the independent variables and that are likely to influence the dependent variable. If y is a variable that depends upon the independent variable x1 to xn, let's say up to xn, then the functional form we can write y is some function of x1 to xn. Write the functional equation in the form, can write y is equal to some constant times of x1 to the power of a, x2 to the power of b, x3 to the power of c, dot dot up to xn to the power of m, that we don't know. Okay, so where c is a dimensionless constant and a, b, c are arbitrary exponents. Express each of the quantities in the equation in the fundamental dimension. Now, each expression we will be writing in terms of the fundamental dimension, that is M, L, T. Okay, this also will be expressed as the form of M, L, and T. Again, all of these terms will be expressing in terms of M, L, and T. Okay. Now, by using the dimensional homogeneity, that means this side also we will be having some power of M, L, and T. And now because the dimensions on both the sides will be equal, that is, it is homogeneous, we obtain a set of simultaneous equations involving exponent x, a, b, c. And formation of dimensionless group by the variables with like components. And we'll see how to do this. Okay. So better let us start with the problem so it will be more clear. Let us consider a frictional resistance force. So there is some frictional resistance force when a liquid is flowing through a pipe, and it depends upon factors like, let us say, it depends upon factors like viscosity, density, velocity of the diameter of the pipe, and pipe surface roughness, let's say epsilon. Okay. Derive a rational equation for the pipe flow in terms of dimensionless groups by Rayleigh's formula. So let us try to do. So we can write something like this. Let's say we have force. So this will be equal to, let's say, some constant C times of mu to the power A, density to the power B, velocity to the power C, D to the power of, let's say, D, and epsilon to the power of E. Okay. Then we will be expressing each of the equations in the form of the fundamental dimension. So if you remember what is force, force is nothing but mass times of acceleration, is nothing but m L t to the power of minus 2. Right? Let me write it in another form so that it will be clear. Okay. I'm writing in this. Okay. So this will be m L t to the power of minus 2. Right? And this will be a constant, so no dimension something. This is viscosity. So if you remember what viscosity was, is nothing but tau is equal to mu into v by y, and this is nothing but force per unit area. Correct? So m L t to the power minus 2 by L square, and here we have mu, and this is meter per second, so L t to the power minus 1 by L. So L and L got cancelled. This is 1 minus 2, so minus 1. I'm rubbing this. And this one also and t to the power minus 1. So this will be coming to this side and it will be minus 1. Correct? So this is the dimension of viscosity. So we can write m L to the power minus 1, t to the power minus 1. Right? Now this we have is density. This is uh, mass per unit volume. So we have m L to the power of minus 3. Correct? This is velocity. Similarly, we can write L t to the power minus 1, and diameter nothing but only L, and similarly this is also nothing but L. Right? So we can write it as, on the left side, let me write this color, helpful. We can write, here it is m L t to the power of minus 2, and this side we can write it as m L to the power minus 1, t to the power minus 1 to the power of a. Okay. And we have m L to the power minus 3 to the power of b. Then we have L to the power LT to the power minus 1 to the power c, then L to the power d, and L to the power e. So let's equate first the power of m. So this side power of m, so m power I'm equating. This side it is 1. This is equal to a plus b. I think that much, right? Similarly, if we equate the power of L, we will be getting 1 is equal to minus a minus 3b plus c plus d plus e. And to the power of time, if we equate, here we have minus 2, and this is equal to minus a minus c. I think that much, right? Okay. Okay. So now we can see that now we have obtained three equations. We have three equations. And how much parameters we have? We see the unknown constants, how much we have. We have A, B, C, D, and E. We have five unknown equations, right? So we cannot solve this completely for now. To obtain exact like power, we cannot obtain to see what is the exact relationship. So what we have to do is we have to obtain it as some function, like some non-dimensional parameters. So let us see. Okay. Oh. So how do we do that? So what? Let us see that what is some variable which is present in all the three equations. You see, a is present in all the three equations. So let us try to express it first. Let us try to express all the equation in terms of a. So the first we can write b is equal to 1 minus a, and here we can write c is equal to 2 minus a, right? Similarly, from this third we have two things, right? We have d and e. So let us write d for now, because here also they have taken d. Anything we can write. E also we can write. But let us try to do with d. So d is nothing but 1 plus a plus 3b minus c minus e. So 1 plus a plus 3 times of b. What is b? 1 minus a minus c. What is c? Minus 2 plus a minus e. So if we simplify this, this is 1 plus a plus 3 minus 3a minus 2 plus a minus e, right? So we have 1, 3, and 2. So this will be 2. We have 2a minus 3a. So minus a and then minus e, right? Minus a minus. So now I think we have expressed almost all the variable in terms of, because we have three five equations, so we will be left out with two unknown parameters. Okay. So now let us express everything in terms of A and E. It's not necessary that A and E should be the variable. Any two variable you can express from your choice. Okay. Now let us see what we can do. So now we have uh, F is equal to, first it will be C times of mu to the power of A rho to the power of B. So B is nothing but 1 minus A, and then we have velocity C, V to the power of 2 minus A, and D to the power of D, which is nothing but 2 minus A minus E, and roughness to the power of E. Correct? Now let us try to get all of them into certain form so that all the like uh, exponents are in the same place. Okay. So we have mu, and then we have minus rho. So let me write it rho. Here also V. Okay. And then we have D. Okay. And this to the power of A. And then we have E. E also we can write epsilon by D to the power of E. And we have rest as terms. So let us take it to this side, which is nothing but this will be rho, and V square is there. So V square will be there. And then we have D square as well. Right? Or otherwise, in the form which is written here, we can write F by rho V square D square is equal to C times of this. I can write rho V D by mu. And instead of A here, I can write it as minus A, and epsilon by D to the power of E. So we can see that all these we have three dimensionless terms. One is this one is this one, and one is this one. These are all dimensionless groups and forming a rational equation. So we can therefore write that this force F by rho V square times of D square is nothing but a function of rho V D by mu, that which is nothing but the Reynolds number, and the relative roughness, that is epsilon by D. Okay. I hope it is clear. Let me write it again. So it's nothing but a function of epsilon by D and rho V D by mu. Okay. So we got a dependency. Like we now know that F by rho V square D square, which is a which is a dimensionless group, is dependent upon other dimensionless groups in this particular form. Okay, now let us see the next method, which is nothing but the Buckingham's pi method. So this one is, if you remember, this is the, let me write it here. So this is nothing but the Rayleigh method. Okay. So the next that we will be studying is the Buckingham's pi method. Okay. So the Buckingham's pi method, it relies on the identification of variables involved in a process, just as previous. But the few of these variables have to be marked as repeating variables. The repeating variables among themselves should not form a non-dimensionless number. So we have to keep in mind. And if a physical process has n variables and from those j are the repeating variables, then there are n minus j independent non-dimensional non-dimensional numbers that that can describe the process. Uh, okay. So let us see how this is done. Let us start. So according to the theory, the functional relationship among the variables x1, x2, x3, again, we can write that if we have x1, x2, up to xn, then this function will be equal to 0. And if j is, let's say, is the number of fundamental dimensions, okay, fundamental dimensions, that is m, l, and t. For this case, we have only three fundamental dimensions. So, therefore, the number of dimensionless groups that we will be forming will be equal to n minus j, where n is the number of variables. Okay. So, let us see how it is done. That dimensionless groups can be expressed as pi is equal to repeating variables to some power and then one independent variable. Okay. And the number of repeating variables should be equal to number of fundamental dimensions. This thing you should note. Number of repeating variables is equal to number of fundamental dimensions. Okay. So let us see. Uh, and generally it is equal to 3. That is j is equal to 3, as in this case we know. But it might not be 3 in all the cases. But for Our case here, it is most probably 3. In most frequently it will be 3 only, but it can be more than 3 as well. Okay. So first is to identify the relevant variables and function, write down the dimensions, establishment of the number of independent dimensions in non-dimensional groups, choose j which is equal to 3 dimensionally independent repeating variables. Generally, the first representing the fluid property, second representing fluid characteristic, and then the geometric characteristic. So you have to choose it wisely. Then create the pies by non-dimensionalizing the remaining variables and by solving the coefficients, setting the setting the non-dimensional relationship, and then rearrange if required for convenience. In this case, you are free to replace any of the pies by the power of that pi or by product of other pies. We'll see that. So let us try to understand this with an example. I think with example, it is better or easier to understand. Okay. Okay. So let us consider the frictional resistance force that we have already discussed. That is F, and it is dependent upon terms. So many terms like, but here we will be writing it like this. Say it is a function of F, mu, rho, V, D, and epsilon, I think, is equal to 0. Right? And all the dimensions also we have noted down. Okay. For mu, we have m L to the power minus 1, T to the power minus 1. This is m L T to the power minus 3. This is L to the T to the power minus 1. And this is nothing but L. Here also we have L. This one we have ml T to the power minus 2. Okay. So if you see what is the number of relevant variables, you see number of variables is equal to 6. 1, 2, 3, 4, 5, 6. And number of fundamental dimensions, that is number of fundamental dimensions, is equal to 3, and that should also be equal to number of repeating variables. Repeating variables. Okay. And then number of non-dimensionless groups, or sorry, number of dimensionless groups will be n minus j, which is 6 minus 3 is equal to 3. So we will be creating non-dimensional group. That is, number of pies should be 3. Okay. So let us start. We have let's say pi 1, pi 2, and pi 3. These are 3 non-dimensional groups. And we will be choosing 3 repeating variables, and we have to choose the repeating variables in such a way that they should not form any, they, like, one dimensionless, like one variable should not be could not be created from the other ones. So that is most important thing, you see. So it is better, like, let us consider one L, any L we can consider. So let us consider D. So let's say one of the repeating variables say is D, because in other terms So if one d is we have considered, we cannot consider epsilon again, because with d dimension we can easily create this epsilon dimension. So the repeating variable should be like that, so that from one we cannot create the other. So let's say the next one we can consider something with L and T. You can see there is no mass in this, so we can consider this V, because you see now we have D and this is V. We cannot create D from V, or we cannot create V from D. And then another we can take anything, said like density, let's say, or viscosity also we can take. It doesn't matter. Okay. So okay. Should we take viscosity? Let us try to take viscosity and see if we are getting any problem. Okay. So I'm considering viscosity. So this has unit of m L1 t to the power minus 1. This has a dimension of L t to the power minus 1, and this has something of L. So we cannot create one from another. That's for sure. Okay. So let us say we are writing here mu to the power of A1, V to the power of B1, and D to the power of C1, and then we have F. Okay. And if you see, F can be created by a combination of all these things, because in F we have what? You see, in F we have M, L, and D. Here we have M, L, and D. Let us see. Then we have mu to the power of A2, V to the power of B2, and D to the power of C2 to the power of rho. Okay. And then mu to the power of A3, V to the power of B3, and sorry, D to the power of C3 times of epsilon. Right? Okay. So let us see. Let us now substitute the fundamental dimensions and let's see what we are getting. Okay. Okay. So here we have m to the power 0, L to the power 0, and T to the power of 0. And for viscosity, we have m L to the power minus 1, T to the power minus 1 to the power of A1. V is L T to the power minus 1 to the power of B1. And then we have L to the power of C1. And what is F? F is mL T to the power minus 2. Correct? So if we equate power of m, this is 0 is equal to A1 plus 1. Right? This implies what? A1 is equal to minus 1. And if we equate L, you see we have 0 is equal to minus A1. So we have L to the power minus 1. Plus we have B1. Plus we have C1. Correct? And then we have T minus A1 minus B1. So this implies we can write B1 is equal to minus A1, and A1 is minus 1. So this B1 is 1. And from here we can get mm, C1 is equal to A1 minus B1. So A1 is minus 1, minus 1. So this is minus 2. Okay. So what we we are getting is pi 1 is equal to mu 1 to the power a1, mm, which is mu to the power a1. Yes, so we have mu to the power of minus 1. We have v to the power b1. b1 is 1. And d to the power c1. So d to the power of minus 2 times of f. Okay. Or we can write something like this. We can write it as f by. So here we have f times of v to the by mu times of d square. Okay. So this is our first pi 1. Right. Now let's see. Let us try to find out pi 2. Okay. Let us try to solve and find pi 2. Uh, oh, okay. So for solving pi 2, again, we can do the same. This implies, let's say, m to the power 0, l to the power 0, and t to the power 0. And this is equal to same m, l to the power minus 1, t to the power minus 1 to the power of a1, l t to the power minus 1 to the power of b1, and l to the power of c1. And then we have rho. Rho is nothing but is m l to the power minus 3. Right? So if we do a balance for m, 0 is equal to a1 plus 1. This implies we got, sorry, this is not a1, this is a2, b2, and c2. This implies this is a2 is equal to minus 1, l minus a2, plus we have b2, plus we have c2 minus 3. Correct? And then we have t. 0 is equal to minus a2 minus b2. There are no more t's. Okay. This implies b2 is equal to minus a2, which is nothing but 1. And then we can substitute here. 0 is equal to minus a2 is plus a2, so plus 1. B is equal to 1 minus 3, plus we have c2, so c2 is equal to 1. Okay. So we can write pi 2 is equal to mu to the power of minus 1, v to the power of 1. I can just write v, and d to the power of c2 is 1. So here we have 1, and then we have rho. So this is pi 2. Similarly, let us try to find out pi 3. M L to the 0, t to the power of 0. This is equal to m L to the power minus 1, t to the power minus 1, a3, L t to the power of minus 1 to the power of b3. Then we have L to the power of c3. And last parameter is d. Okay. So we have again L to the L will be there, right? Not no power L. Okay. So we'll do a balance. M will be 0 is equal to minus A3. So there are no more M. This implies A3 is nothing but 0. L 0 is equal to minus A3 plus we have B3 plus we have C3 plus 1. Correct? And T we have 0 is equal to uh, minus A3 minus B3 is okay. Since A3 is already 0, so we can write B3 is nothing but 0, right? And therefore C3 will be equal to nothing but minus 1. So we can write pi 3 as mu to the power of 0, v to the power of 0, t to the power of minus 1 and epsilon. That is nothing but epsilon by t. Right? So what we got dimensionless parameters. So now we can do a rearrangement something like this. So we can write we have a function of f by f v by mu d square, f times of v by mu times of d square. Second one is okay. Second one is rho v d by mu, and then we have epsilon by d is equal to 0. Right? Now you must be thinking, okay, if we compare the pi's of both the terms, right? Say this is our pi 1, this is pi 2, and this is pi 3. So these are also dimensionless, non-dimensional group. But what we got from here, let us write it this color, okay, is something like this, a function of f by rho v square times of d square. We have then pi 2 is nothing but mu by rho v d, and then we have epsilon by d, okay, is equal to 0. But you see, we got this as the pi 1, this as the pi 2, this as the pi 3. But how are they? Both of these expressions give you the same kind of relationship or not? Actually, they do. And how do we do that? Let us see how we can obtain, like, are we missing something, or are both of these expressions representing the same this thing? Okay. Okay. Now you see, this is a functional relationship, right? What do you mean by functional relationship? Thus, this dimensionless term is actually some in some expression we will be getting some constant to the power this, to the power this. Like we have f v by mu d square to the power some function is equal to some constant to the power in times of rho v d something something to the power of something something we will be getting. Okay. So now, if you see, what I will be doing is I will be multiplying both, I will be dividing both sides by v square. Okay. So if I do that, you see, here I will be multiplying with v square. Okay. Uh, okay. Let me write it in this way. I'm rewriting it here. So we can write this as we have already discussed, that this f v by mu times of d square is equal to, I'm writing it some another function of, let's say, f dash of rho v d by mu, and this will be epsilon by d. Okay. So if you see, I divide both sides by v square. So here it will be v square, and here it will be, say, v square. Okay. Not v square. Let me take v cube. I'll take. So if I divide by v cube, this is v cube and v cube. You see, this v and v will cancel out. This will be v square, and here also we will be getting v square. Correct. So this and this, now I can remove this v. This d will be there, and this v cube I'll divide. This v square will come here. So this v square I'm removing, and I'm writing it here. This is v square, and here also v square. Now what I will be doing is I'll be yes. Now what I will be doing is I will be multiplying with d square, uh, dividing by okay, d square here already it is there. So I'll divide by rho. Let's say I'll divide by rho. Okay. So here also it will be coming rho, and then I'll multiply with mu. So this mu and mu got cancelled out. This rho and rho will be cancelled out. And then we have okay. So now you see, this side we actually arrived at f by rho v square times of d square. Here also, if we do similar simplification, you will be getting rho v and d by mu, and this epsilon by d term will be there. So if we just simplify it, you know, you will, you can, from this expression you can still get this particular form of the expression. So both of these expression basically represent the same kind of relationship. How you obtain that expression, it doesn't matter. Both of these expression actually represent the same thing. Okay. Okay. So let us try to solve one question. Okay. So flow resistance of a sphere. The drag d of a sphere is influenced by the sphere diameter. So let us write the drag d is influenced by sphere diameter d. Okay. So drag is nothing but the force. So I'm writing drag is influenced by sphere diameter d, flow velocity u, fluid density rho, and fluid viscosity mu. So we can see that there are number of variables is equal to 5. Fundamental dimensions are 3. So number of non-dimensional groups will be n minus j, that is 2. So we will be creating pi 1 and pi 2. So let us say fd will be there because it is one of the dependent variables. Let us consider d, okay, is 1. Mm, this thing, this d, d is what is the diameter, right? So d to the power a1, u to the power of b1, and let's say rho to the power of c1. So d to the power a2, u to the power b2, and rho to the power of c2, and then let's say mu. Okay. So if we do this, this is m l t to the power of minus 1. Sorry, this is not m, this is l a1 and l to the minus 1 b1, and this is m l to the power minus 3 to the power of c1, right? And this is the force, that is m l to the power minus m l to the minus, wait, what is force? M l t to the minus 2, right? T to the power of minus 2. Correct. So we have, if we do m, then it will be 0 is equal to c1 plus 1. This implies we got c1 is equal to minus 1. L is nothing but again 0 is equal to a1 plus b1 minus 3 times of c1 plus 1. And t is nothing but 0 is equal to minus b1 minus 2. So b1 is equal to minus 2. And therefore we have a1 is equal to b1 is minus 2 minus 3 plus 3 plus 1. So this is nothing but this is 4 minus 2. So a1 is equal to minus 2. Okay. So pi 1 is equal to d to the power a1. So d to the power of minus 2, u to the power of b1. So u to the power of minus 2, rho to the power of c1. So rho to the power minus 1, and ft. So we can write pi 1 is equal to fd by rho u square d square. Okay. Similarly, for the second case also we can do, that is L to the power of A2, L t to the power minus 1 to the power of B2, m L to the power minus 3 to the power of C2. And then we have viscosity. Viscosity has dimensions of ml to the power minus 1 t to the power minus 1. M L to the power minus 1 t to the power of minus 1. This is equal to, so if we do for m, 0 is equal to C2 plus 1. This implies we have C2 is equal to minus 1. L for L, if we do 0 is equal to A2 plus B2 minus 3 times of C2 minus 1. And T, if we see, minus B2, and we have minus 1. This implies we have B2 is equal to minus 1. So 0 is equal to A2 uh, minus 1 plus 3 minus 1. So 3 minus 2, that is 1. Therefore, A2 is equal to 1. Sorry, A2 is equal to minus 1. So we can write pi 2 is nothing but mu, sorry, not mu, we have d to the power of minus 1, u to the power of minus 1, rho to the power minus 1 times of mu, which is nothing but mu by d u rho. So we can write functional form of fd by rho u square d square, rho u square d square, and mu by d u rho is equal to 0. Or otherwise also we can write this fd by rho u square d square is equal to some function of mu by rho u d. Okay. Similarly, you can try this next question. So this can also be solved similarly. You can try to solve this question. So here we will be having 4 non-dimensionless parameters. Okay. Okay. And you can also try to solve this question Here also there is one interesting thing. You can see the number of variables here are 3, and number of like fundamental dimensions are also 3. So instead of j is equal to 3, here j will be is equal to 1 less. Okay, that means 3 minus 1, that is 2. And therefore the number of non-dimensionless or the non-dimensional group will be 3 minus 2, that will be 1. Okay. Okay, now let us consider about this we have all discussed about dimensional analysis. And next we will be looking at the similitude. Okay. Okay, let us see if we can start and solve some questions, and then again we will be going back. Okay. Okay, so let us see. So force, this force F that we see here is nothing but a what kind of fundamental unit? So we know it is a conventional convenient fundamental unit. And then what is the dimension of surface tension? Surface tension is nothing but force by length, right? So force is m l t to the power of minus 2 by l. So this will be m t to the power of minus 2. Now, if there are n variables in a dimensionally homogeneous equation, and if these variables contain m primary dimensions, then the variables can be grouped into how many? That is n minus m non-dimensional groups. Okay. The velocity of sound c, so velocity c varies with pressure, density. Using the dimensional analysis, is it possible to relate the quantities as c is equal to some constant into square root of? Is it possible or not? So that is something we can check. Okay. So let us see. So pressure is nothing but force per unit area, that is m l t to the power minus 2 by l square. So that is m l to the power minus 1 t to the power of minus 2, right? And density is nothing but kg per meter cube, or we can write m L to the power minus 3. So if we substitute in this, we have pressure is m L to the power minus 1 T to the power minus 2 divided by m L to the power minus 3 and the square root of this. So if we see, let me remove this. So this is m and m got cancelled. So this is L square and T to the power of minus 2 square root of this, and this will be L T to the power minus 1, which is nothing but dimensions of velocity. So you can see that yes, it can be represented using this form of the equation. So what is the dimension of kinematic viscosity? So kinematic viscosity we know is nothing but mu by rho, okay, ml to the power minus 1 t to the power minus 2, okay, divided by m L to the power minus 2. Sorry, L to the power minus 3, right? So this will be, okay, this will be minus 1. So here we see this got cancelled out. So it will be L to the power of 2 T to the power minus 1, right? Okay, let us see the next question. In Buckingham's method, the dimensionally independent repeating variables generally represent fluid property. Then we have fluid characteristics and geometric characteristics as well. So both A and B are the correct option. Now, the drag of a sphere is influenced by what are all the parameters that we know? Mu, okay, fluid density, fluid viscosity, then we have diameter, flow velocity, all these parameters it is dependent upon. So both A and B, right? So it is given the Brinkman number is often used to describe the flow of organic and viscous liquids. It defines the ratio of viscous dissipation to heat conduction in fluid. It is a combination of fluid viscosity mu, velocity v, thermal conduction k, and fluid temperature T. What should be the derivation of the Brinkman number, which is proportional to viscosity? So, which one is the correct expression for Brinkman number? Okay, so let us see. So, how do we know? So, you can see which of these expression actually satisfies this non-dimensional non-dimensional form. Okay. So you can see one we have mu then v square or mu square by v square, whichever if you substitute it will give a non-dimensionless or non-dimensional form, and that is the correct expression for Brinkman number. So this is the correct expression. Okay. The Buckingham's method and Rayleigh method of dimensional analysis determine only relevant independent dimensionless parameters and not the exact relationship between them. Okay. The pressure difference across a soap bubble related to the radius of curvature of the soap bubble as delta P is equal to some constant rho by d, right? And is therefore Mhm. to radius is inversely proportional to the radius. Correct. Auxiliary fundamental dimension unit for measurement of magnitude light intensity is candela. And then we have question from similarity, okay, which we will be discussing. Okay, so let us see. Let us discuss about the next part, that is similitude and its classification, and the importance of dimensionless number and their significance, and then model analysis. So similitude is a concept that is applicable for testing engineering models. Like, say for example, we have a large system where we cannot perform any work. So what we do is we create a small model and we do all different types of tests in that model, and then using these non-dimension or the dimensionless groups or the non-dimensional numbers, we then expand those concepts to the real world prototypes. Okay. In order to have the complete idea about the flow device, it is very essential that the model should represent its prototype completely and fully in all aspects. Therefore, the similarity between the prototype and its scale model is known as the hydraulic similitude. Overall, the condition that a model of a phenomenon reproduces all aspects of behavior of the prototypes represented by it is known as the condition of similitude. We used to describe the behavior of other similar system in real world and outside the laboratory. So two systems described by the same physics operating under different sets of conditions are said to be physically similar in respect of certain specified physical quantities. The ratio of corresponding magnitude of these quantities between the two systems is the same everywhere. Okay, so let us try to solve this question. Consider a submarine modeled as 1 by 40th scale. So we can write LR, that is nothing but prototype by, sorry, not prototype, is nothing but LM by LB, okay, is nothing but 1 by 40. The application operates in seawater at 0.5 degrees Celsius. So the prototype operates in seawater at 5 meters per second. The model will be tested in fresh water at 20 degrees Celsius. Find the power required for the submarine to operate at the stated speed. So, what is the power that is required? So, you see, first we have to do a dimensional analysis is used to rearrange the units to form the Reynolds number. So, we have Reynolds number. So, the dimensionless number account for all the variables listed above except f, which will be the last test measurement. Since the dimensionless parameters will stay constant for both the test and the real applications, they will be used to formulate scaling laws for the test. So we can equate the Reynolds number. So if we do that, so uh, we can just substitute the values and we can get V model equal to V application times of 2.19. And similarly, the application force is equal to 21.9. Okay. And now you can calculate the power, that is nothing but force into velocity. In the similarity of forces, both the geometry and kinematic similarities are necessary for dynamic similarity. The dynamic similarity can be assumed to exist if the ratios of all forces acting on corresponding fluid properties, fluid particles, and boundary surfaces in model and prototype systems are the same. Okay. That means Reynolds number of the model should be equal to Reynolds number of the prototype. And these are the different kind of dimensionless number. One is the Reynolds number, one is the Froude number, and another is the Weber number. So I think you can Mach number is also there. So I think you can easily understand all the dimensionless numbers. Okay, so I think we have covered all the topics. So we'll end the session today and we'll discuss more about next lecture coming next Friday, and we'll be solving and discussing more questions. Okay, so thank you.